Railways around the world have replaced jointed tracks with continuously welded rail, changing the way railways are constructed and maintained. By the end of this video, you'll understand why this switch happened and how it has improved rail safety, speed and comfort. Together, we'll cover the drawbacks of jointed track, the advantages of welded track, and the challenges of both. Let's get into it. Jointed track takes its name from the fish-plated joints used to join lengths of rail together to form the surface on which train wheels can run. To form these joints, the rail ends are drilled, fish plates put in place, and bolts passed through to tighten it all up. And it worked, and it still does. These regular joints are what give the classic clickety-clack sound associated with train travel. But while it does work, jointed track has a number of pretty crucial drawbacks. First and foremost is the safety side. The joints are effectively breaks in the rail, and this leads to a concentration of forces on parts of the joint, namely the bolts and the fish plate. Broken fish plates, cracks from the bolt hole that lead to rail breaks, and also vertical movement of the track at the joint are all risks that can lead to serious incidents. Then there is the maintenance requirements. Joints need looking after. The bolts need checking to ensure they stay tight and hold the joint together. The gaps between the rail ends need to be maintained at a set width to allow for thermal movement of the rail, and the fish plates need lubricating to allow that thermal movement to happen unhindered. There is the rail ends that are susceptible to rail defects, such as rail end batter. So this is not an exhaustive list, but you can already see there's a lot to be thinking about. And then, lastly, there is the comfort factor. With the regular clickety-clack sound comes the regular bumps for the train. Maybe not so much for the newer passenger trains with soft, smooth suspension, but for a freight train, it's got to be noticeable. And the noise. Living next to the railway with a regular sound coming from the track every time a train goes past, even if the joints aren't voiding, isn't nice. Before we get to the solution to all these problems, if you're interested in the railway and track engineering, I have a free Guide to Cant ebook that's for you. Cant is a fundamental part of how the track is designed and is definitely something you need to know. So hit the link in the top right hand corner or the description below to get your free guide now. So bring in continuously welded rail, the saviour. Let's first look at what we mean when we say continuously welded rail. I mean, the name does cover it very well, to be honest. A continuous rail, and therefore a wheel running surface, is created by welding lengths of rail together rather than jointing them. When the welds are correctly ground off, the running surface is smooth for the wheel, like a newly laid road. There are two main types of welds used to create CWR. There is the alumothermic, or simply thermic welding, which involves using a chemical reaction to create molten metal and effectively casts the weld between the two rail ends. Then there is flash butt welding, which uses high electrical current passed through the rail ends to heat and join them together. So what are the advantages of CWR that make it such a game changer? Well, there's quite a few. When a joint is removed from the rail, it removes a weak point. So, by removing thousands of joints, thousands of weak points and potential failure points are removed from the track. This reduces maintenance costs, as all those jobs we spoke about earlier no longer need doing, and increases reliability as those potential failure points are removed. It also means that staff don't need to go on track as often. Then there's the safety aspect. Removing the joints removes a serious risk to passengers and trains. If a joint fully breaks, as in both fish plates break and the rail ends are free to move, it's effectively a broken rail, which is a huge derailment risk. So, again, remove the point of failure reduces the risk dramatically. By creating a seamless running surface, CWR also improves the ride quality for trains, as well as allowing them to travel at higher speeds. Lots of countries, including the UK, have higher maximum speeds for CWR track than that of jointed. It would be false to say it's all positive though. CWR does have some challenges with it. There is the heat. Long, continuous pieces of metal will expand when they get hot, and the forces involved can get very high. To prevent track buckles, the rails are stressed. This involves stretching the rails to the length they would be at a higher temperature. This puts them in tension, which means as they heat up, this tension decreases before they go into compression and the thermal forces start to build. Then there is installation. Changing and installing new rails in CWR does involve more work. Welders have to be there and have enough time to complete their work, as the quality of a weld is vital. Then there is the stressing I just mentioned, another process that needs to be undertaken. Contrast this with in jointed track, where it's a case of removing the bolts from the joint, changing the rail, drilling new holes, and then replacing the bolts. You can kind of see where I'm coming from, but I think you'll agree that the positives of CWR really outweigh these few challenges. This is evidenced by the fact that the various high-speed rail networks across the world use or are going to use CWR. So now you can explain all the issues with jointed track that CWR solves, as well as some of the challenges CWR has of its own. On screen now are some more videos from the PWay engineer that you might find interesting. Do check them out. Please do remember to hit that subscribe button and also give this video a like. Thank you.